So now we are going to look into a question which goes as follows. Design an ideal low-pass filter with specifications as follows. HD of omega is equal to 1 for 0.5 pi less than or equal to omega, less than or equal to 0.5 pi, and 0 elsewhere. Find h of z for n equal to 5. So when we design a digital filter, the ultimate aim of the digital filter is to find the transfer function of that system. So I think in the previous video I already mentioned to you about transfer function. What is transfer function? It is a ratio of y of z by x of z, and it is that property of the system which defines the output, or rather it is the z transform of h of n, which is the impulse response of the system. So h of z is a property of a system, and here we have to design a filter, an ideal low pass filter, and eventually what we are going to do is we are going to find out h of z. So moving on, the first thing that we need to get an idea is regarding how this filter exists. So we'll be making use of the graph. So I'll be using this one. So this is going to be the graph of HD of omega, that is a frequency response. So over here, the y-axis we have HD of omega, over here we have omega, and our ends will be represented by minus pi and plus pi, because our frequency response will span in this region of 2 pi, which will be from minus pi to pi. So if you have a doubt why we are taking from minus pi to pi, it would be the same if we take the response from 0 to 2 pi. Only the bit of the things will be different. That means this part will be shifted over to the other end. Rest everything will be same. So for a convenience sake, we are taking the span from minus pi to pi to cover up this 0.5 2 pi span. So as per our response that is given, HD of omega is 1 for this much region. So we'll have a cutoff frequency. So we have a cutoff frequency omega c specified over here, that is 0.5 pi. So we have a 0.5 pi over here, and it will be equal to 1 in this span, and the rest it will be 0. Now compared to the other part, the other half, there will be another cutoff frequency, that is 0.5 pi, and that to 0 will be equal to 1, and the rest will be 0. So the first step in our filter design will be to estimate the frequency response of the filter using the specifications given in this particular question. To sum up what will be happening in this program, we can make use of this diagram over here. So you are given HD of omega using inverse Fourier series or the inverse Fourier transform concept. We'll convert HD of omega to h of n, and that h of n will be converted to h of z using z transform. So like I said before, the ultimate aim of designing a filter will be to find out the transfer function of the system, which is h of z. So the next step that we are supposed to do is conversion of HD of omega into HD of n coefficients, and for that we are using this inverse Fourier series equation. So we have HD of n equal to 1 by 2 pi integral minus pi to pi, this is pi, HD of omega e raised to j omega and d omega. So moving on, if we have to further solve it, we have to consider the span that is given over here. So we have the span from minus pi to pi, which is why we draw this graph to analyze it. In this span of minus pi to pi, only this span is valid with a value of 1. That is minus 0.5 pi to plus 0.5 pi. So we can modify this equation to minus 0.5 pi to 0.5 pi, and HD of omega in that span is equal to 1. So it can be reduced to e raised to j omega and d omega. So moving on, we can write it as 1 by 2 pi, and few concepts that you can remember for this solving of equation will be integral of e raised to j omega and d omega will be equal to e raised to j omega n by jn. So when we go to solve this particular thing, it becomes e raised to j omega n by jn. minus 0.5 pi to plus 0.5 pi, and when we solve this particular thing, the omega will be substituted with this value, so eventually it is going to become 1 by 2 pi jn. The jn is taken common, so we can write it as e raised to jn 0.5 pi minus e raised to minus jn 0.5 pi. You can use this pi or this pi for your equation, not an issue, but eventually you should get it correct. Now this is something that we are already familiar with. We know the equation for e raised to j theta, that is cos theta plus I sin theta, and we know the equation of e raised to minus j theta, which is cos theta minus I sin theta. So when you subtract this, the result will become this, and this will get cancelled. It becomes 2I sin theta. So as we move on, when we try to solve this particular problem, we get it as 1 by 2 pi jn into 2j sin n 0.5 pi. So this can be reduced as this 2j and this 2j will get cancelled. So it becomes sin n 0.5 pi by n pi. This is a general equation for h of n, and what we need to do next is we need to find out the coefficients of h of n. Now you have a part in your question where your capital N is equal to 5, which means your h of n will be containing 5 samples, and those samples will be from the range of minus 2 to plus 2. So it will have 5 samples: h of minus 2, h of minus 1, h of 0, h of 1, and h of 2. So this will make up your h of n, and we'll have to substitute the value of n in this equation to find out these coefficients. So being the first time, we'll take a look at individual one. So as we move about to find out the coefficients, I have already done 4 of them over here. So h of minus 2 will be equal to, if we substitute minus 2 in this equation, it becomes h of minus 2 in h of minus 2 into 0.5 pi, it becomes h of sine of minus pi whole divided by minus 2 pi, and this becomes 0. 0 by minus 2 pi becomes 0. H of minus 1 will be equal to sine of minus 0.5 pi by minus pi. When you substitute minus 1 over here, this will become the equation. So it becomes minus 1 by minus pi equal to 0.318. Here comes another strange fact. I am going to find out these two coefficients, that is h of 2 and h of minus 1. So as you can see over here, when you compute this particular equation again, you will get this value as 0 and you will get this value as 0.318, which is same. H of minus 2 will be equal to h of 2, h of minus 1 will be equal to h of 1. Now I am going to find out h of 0. Now we will have to learn about L'Hospital's rule and its application over here. Why do we need L'Hospital's rule? Okay, out of these 5 coefficients, we have found out 4 and its corresponding values. We have to find out the last one, h of 0. So when we substitute 0 over here, we can see that it becomes sine n 0 into 0.5 by 2, 0.5 pi whole divided by 0 into pi. So we are getting a divide with 0 case out here. So that cannot be solved as it is. So we need to apply L'Hospital's rule. And as per L'Hospital's rule, this is a rule, L'Hospital's rule. So when we apply L'Hospital's rule out here, you can see that limit n tends to 0, sine n theta by n theta becomes equal to 1. So which means we need to apply L'Hospital's rule to this particular equation of h of 0. So it becomes sine n 0.5 pi by n pi. So if this is n theta, then this should also be n theta. So these two terms must be made equal. What we are missing over here, a 0.5 term. So if a 0.5 is multiplied at the denominator, it has to be multiplied at the numerator also. So this equation becomes 0.5 into limit n tends to 0, sine n 0.5 pi by n 0.5 pi. So it becomes 0.5 into 1 equal to 0.5. So we have found out the h of n coefficients. So h of n coefficients will be as follows. It will be 0, 0.318, 0.5, 0.318 and 0. So this is your h of n coefficient. So the equation of the transfer function, which is a final step, h of z will be given by h of 0 plus summation n equal to 1 to n minus 1 by 2. This is 2. H of n, z raised to minus n plus z raised to n. So when we open the brackets, we can expand it as follows. H of 0 plus summation n equal to 1 to 2. H of n, z raised to minus n plus z raised to n. So when we open the brackets, we get h of 0 plus h of 1, z raised to minus 1 plus z plus h of 2 into z raised to minus 2 plus z raised to plus 2. But we know h of 2 and h of minus 2 are 0. So eventually our final equation will be like 0.5 plus h of 1 is 0.318, z raised to minus 1 plus z. So our final transfer function will be 0.318z plus 0.5 plus 0.318 z raised to minus 1. And there is one more step for this particular thing. That is, what we have done is we have obtained the transfer function over here. Without doubt, we have obtained the transfer function. But there is another one thing that we need to obtain, that is a realizable transfer function. To obtain the realizable transfer function, what we need to do is this h of z, or we'll create a new h dash of z, and this h of z must be multiplied with z raised to minus n minus 1 by 2. So that means it will be equal to z raised to minus 2 into h of z. So that will be equal to, when we look at this particular equation, it becomes, when we multiply this with this term, it becomes 0.318 z raised to minus 1 plus 0.5 z raised to minus 2 plus 0.5 z raised to minus 3. So eventually this becomes our final transfer function, 0.318 z raised to minus 1 plus 0.5 z raised to minus 2 plus 0.5 z raised to minus 3. This is a transfer function, or the realizable transfer function. This in total sums up a transfer function realization, or we have come to the end of the particular problem. So we started with design an ideal low pass filter, and our specifications are given over here, and we are asked to find out h of z for n equal to 5. So I need you guys to do out a tutorial problem. This will be the tutorial topic. So the topic will be the same question, or I'll give you a new one. This is your tutorial question. So the question is, design an ideal low pass filter with specification as follows. HD of omega is equal to 1 for the same frequency specification, but here h of z will be found out for n equal to 11. So you have to do this particular problem as your tutorial.